F322, question 5, June 2012. Here we've got a question all about methane and ethane. You've got enthalpy, you've got green chemistry again, and at the end you've got radical substitution. We start off here, methane manufactured by carbon dioxide and hydrogen, and producing water as well. It wants you to look to find the enthalpy change of the reaction, so what the enthalpy change is here for this reaction is using bond enthalpy. So we've got what we call a burp calculation. So bond enthalpy, reactants minus products. The key thing with bond enthalpy calculations are actually quite nice. It's just adding things up and taking them away. You've got to make sure that you draw out the displayed formula for each of your reactants and your products. So you draw yourself out a nice little formula where you've got carbon dioxide, 4 hydrogens, a methane, and 2 waters. Then you count up the bonds on the reactant side and on the product side. So bonds broken on the reactant side, you've got 2 C double bond O, so 2 times the value in the table, and you've got 4 HH bonds, so 4 times the value in the table. Total those up. On the other side, you've got 4 CH bonds, so times by the value in the table, and you've got 4 OH, 2 OH bonds in each water, so 4 OH bonds in total, and you add those up as well. Then you take burp reactants minus products, and you should come to an answer of minus 162. The key for that question where people go wrong is they don't draw out the displayed formula of their actual equation, and so you get the adding up a little bit wrong. You forget to time something by 2 or something like that, and you lose marks there. So it's critical that you draw out this equation. Even here, possibly you'd want to draw out 4 H to H bonds, and here possibly 2 water molecules, so that you can clearly see how many OH bonds you've got. But that's the key to this question. Once you recognize bond enthalpies, you use the burp, so bond enthalpy reactants minus products, and then you draw the displayed formula for the equation. That's what helps. And then it's simply bonds broken minus bond made, or reactants minus products. Next, we've got a couple of straight green chemistry questions. It tells us that methane is a greenhouse gas, and that scientists are concerned about the concentration of methane increasing in the atmosphere. Now, it wants you to explain how atmospheric methane molecules can contribute to global warming. So the first thing that they do, they're absorbing infrared radiation. It's the first job. They're taking in that infrared. Then they're going to re-radiate that radiation and keep it at the Earth's surface rather than letting it go out into space. But the key thing here is that when you get that infrared radiation absorbed, it's not the molecule absorbing, it's the bonds that vibrate when they absorb that radiation. So that's the critical second thing that you need to say there, the bonds vibrate. If you're talking at all about global warming and molecules in the atmosphere, that the bonds vibrate is often the key thing in the mark scheme. Then you've got a question about CCS, carbon capture and storage, and it wants you to describe 2 techniques. Now for these 2 techniques, we've got 3 that you should know, and you need to know these off by heart. The first one, injected or stored, and it's got to be deep in the oceans, stored underground and I wouldn't, they actually not happy with this here. you want to say here, in place there of, it's porous. Sorry, that's writing terrible, isn't it? You want to say porous rocks. Oh, it's my pen's going mad again. You want to say, sorry about that, and I've lost my cursor now too. You want to say here, porous rocks, not just rocks. There's got to be space for the CO2 to actually get into those rocks. Best to go for mines or disused oil wells or disused mines, so stored underground in porous rock mines or oil wells. A nice easy one, stored by reaction with metal oxides to produce carbonates. That's a good one if you've got the equation there that you can put in as well. So those two techniques, deep in the oceans, underground in disused oil wells, stored by reaction with metal oxides. You need generally two. There are three that you should learn. The final part of this question then, it's told you at the start it wanted to use ethane, and here it is. Ethane reacts with bromine in the presence of UV, so you're thinking immediately radical substitution. It's forming two products, so you've got to make sure that you highlight these two products that are being formed and make sure you read the question carefully to get those two products. I apologise, my pen has got a mind of its own at the moment. So you've got to try and find or get yourself those two products. In this case, it's quite nice and easy because they come out straight away. Describe the mechanism of the reaction. Include in your answer bond fission, equations for each step of the reaction, and name of each step of the reaction. So it gives you those bullet points for a reason. Go through and make sure you tick them off and you've done the question. And your answer needs to be clear and well organized using the correct terminology. So I've started off here straight off. What's the mechanism name? Radical substitution. Then initiation, it's bromine you're using, so bromine in the equations. Bromine goes to two bromine radicals. Of course, the condition is UV, and I'm not quite sure if I've got that written in already. So I'll just add that in if my pen doesn't go completely crazy. Here we've got added in that the condition is UV. And yeah, I'm not doing very well here, am I? Then, bond breaking is homolytic, so I'm ticking off my bond fission there. So I've done that. Yeah, I'm going to stop using the pen. Then I've got propagation, so I'm naming again, which has asked me to name each step. I've got ethane plus my bromine radical gives me my C2H5 radical plus HBr. Note that's one of the things it wanted me to actually get from this reaction. Then with my second propagation step, I'm putting the radical I made here back in the start. Br2 in the next step goes to C2H5Br, which is also, they wanted me to make bromoethane plus bromine radical. Then finally, to terminate, my radicals join. I've got a delightful little scribble on my screen there. It's not letting me rub it out either. Here we go. Oh no. These disasters happen when you're so close to finishing. Anyway, right, so you've got the termination step, two bromines meeting, and here you've got a bromine and a C2H5 meeting to make your bromoethane. So I've made the two things that I need to make in the question. I've just checked that I've ticked off my bullet points. So I've made bromoethane, I've made hydrogen bromide, I've stated what the bond fission is, I've got an equation for each step, and I've named each step. It's also, surprisingly enough, relatively well organized in the sense that I've just said what the mechanism is, and I've gone through initiation, propagation, termination. Now, you can see where I'm getting my marks here. 2 for my propagation steps, 1 for my termination, and if I get all 3 names correct, they could be nice to me here, I'm getting 2 marks for that as well. So that's all good. This is a straightforward, nice question. If you get a nastier one, stick to the formula. Initiation, breaking that radical down, then propagation, you use the radical, you take a hydrogen off, and you make HBr or whatever it is, you get that bromine radical to take a hydrogen off. Whatever this molecule is, take a hydrogen off. Then you put that radical you've made back in with your bromine or whatever it is that was in your initiation step, and you finish it off. Finally, my last question, give 2 reasons why there are many organic products for the reaction here between bromine and ethane. You've got more than one substitution can occur. So I could have bromoethane that then goes back to make dibromoethane, etc. Another thing you could say is that looking at the termination steps, I've only got 2 termination steps. I could have put different termination steps in there. I could have got a C4 molecule, for example, if these 2 had met, 2 of those radicals had met. So you've got that there's lots of termination steps. And finally, you've got products from the termination steps might also react with radicals. So you've got it covered there if you're saying that there's more than one substitution, lots of termination steps, products from termination reacting back. It all goes a bit crazy as it's a chain reaction, so you can't just get one product. It's very difficult to get just a single, or impossible to get a single product from this reaction.